For this lesson, we're working on applying our factored form of the quadratic to be able to solve problems. Before we get into the actual problem solving, though, we're going to start by stating the x-intercepts, or the zeros, of each of the following quadratics. So this reaches back a few lessons ago. We talked about the factored form telling us the zeros, and we said always look at what the sign opposite to what's in here. So when we have a factor of x take away 3, it means we actually have an x-intercept at 3, 0, 3 comma 0. And if we have another factor here of x take away 8, that gives us an x-intercept at 8, 0. So we switch the signs on those. So we can do that for each one of these, switch the sign, and that will give us the zeros for each, or the x-intercepts for each of these quadratic relationships. So fill this in. You don't need my help, I'm sure, for this. Maybe E, but you should be good. Put the video on pause, get those answers, and then you can check your work. All right, so hopefully you've gotten the same answers that I have. I just want to highlight E, because E is one that students sometimes have trouble with. It's the 2x in the front. Remember, the 2x could be written as a 2 and then x take away 0. So that makes your x-intercept here at 0. So 0, 0 is your x-intercept. It's going to go through the origin. All right, let's put this into play here with our first example. A football is kicked from ground level. So it's on the ground, it's kicked off the ground, its path is given by this relationship right here, where h is the ball's height above the ground in meters and t is the time in seconds since the ball has been kicked. Our first step here is we're going to actually take this relation, which is written in what we call standard form. That expanded and simplified form is your standard form. We're going to take that and write it in its factored form. So if you think of your chart, your summary chart that we did, we had talked about always look for a common factor first. And in fact, excuse me, I'm going to common factor the negative 4.9 out of, and t is common as well, negative 4.9t out of both of those terms. There's only two terms there. So I know the first thing would have to be a t, because negative 4.9t squared divided by negative 4.9t would just leave us with t. And then if I take 22.54 divided by negative 4.9, that's going to give us a negative 4.6. Okay, so I made those numbers nice, or not too bad anyway. And so there we are. So that's my common factored form. And I only have a binomial left in my bracket, and it's not a difference of squares because I don't have perfect squares there. This is done in terms of its factored form. Part B is asking for the zeros, or the x-intercepts. So this relates back to the very first question where we were stating our x-intercepts, or zeros, of the relationship. So if I look at my equation that I have here, I could state that this t really would be a t take away 0. It's going to give me an x-intercept, or t-intercept, at 0, 0. And my other one is going to be at 4.6, comma 0. So my zeros are going to be at 0, 0 and at 4.60. So that's the reason we get the factored form. Well, who cares? What do the zeros tell us? What do the zeros mean in terms of the football being kicked? So if we think of this parabola, we know the parabola opens down because of the negative here, or the negative here in the original relationship. We know it opens down. And we know where those x-intercepts are. So if we think of a little sketch here, here's my time axis, here's the height. It's going to pass through 0, 0, and it's opening down, and then it has another positive x-intercept, or t-intercept, here at 4.6. So time 0 and time of 4.6. Well, at those spots, the height is 0. That's why we're calling these zeros, or x-intercepts. They're zeros because the h value, the y value, the h value in this case, is equal to 0. So it means these are the times when the height is 0, or when the ball is on the ground. So I've just typed up a summary there. They represent the times that the ball is on the ground. The ball starts on the ground at a time of 0 seconds and then lands back on the ground at 4.6 seconds after it was kicked. So hopefully that's making sense so far. Now the next question asks, at what time does the ball reach its maximum height? Now again, we've already covered this type of scenario before, or this information before. We know that parabolas are symmetrical. So there's that axis of symmetry that's going to cut that parabola into two equal pieces, and on that axis of symmetry will be the vertex. So if we think of symmetry here, we know that the t, or the time, the t coordinate of the vertex will happen halfway in between the zeros. So the time where it's going to reach its maximum height comes from the midpoint of 0 and 4.6. And to get midpoint, remember we just add the two values together and divide by 2. It's our average. So add the zeros together, divide by 2, and you're going to get 2.3. It reaches the maximum height 2.3 seconds after it was kicked. So we want to use the symmetry to our advantage here with parabolas. Now the next question here, if I can get this to move. Oh shoot, that was not good. That's not what I meant to do. Darn it, darn it, darn it, darn it. Okay. All right, when in doubt, just put it on the next page, except I didn't copy everything over because I really wasn't sure how to do that. So I've just sketched my, excuse me, my curve again and wrote down what the time was to reach the maximum height. So we know that the ball gets to its maximum height at 2.3 seconds. To get the actual maximum height of the ball, we're going to take that time that we figured out here, that 2.3 seconds, which lies on the axis of symmetry, and we're going to sub that into the actual equation that we were given. So the equation we were given was h equals negative 4.9 t squared plus 22.54 t. So we're going to sub in t equals the 2.3 to figure out the height at that particular time. So you just put in your 2.3, you're going to square that and multiply it by negative 4.9 and add the 22.54 multiplied by the 2.3. I just put that in my calculator all in one calculation and get an answer there. And when I do that in one calculation, I get 25.921 on my calculator. So the maximum height of the ball is almost 26 meters, so 25.92 meters. All right, our last part to this question is express the relation in its vertex form. So remember, the vertex form is what tells us the vertex, as well as your width and direction of opening here. So I'll just write in the generic vertex form to remind you of that. The generic vertex form looks something like this. We have the h for the x-coordinate of the vertex and the k for the y-coordinate of the vertex. The a value here will be exactly the same as the a in our original relationship. So our original relationship in standard form, the first term is the negative 4.9 t squared, so the a value is that negative 4.9. So when I state this, I'm going to use h instead of y because it's height, to put context to it. And then negative 4.9 is the a value. The x-coordinate of the vertex is really the 2.3 that we figured out above. It's actually, I don't want to use x, I want to use t. T minus the 2.3. So remember, we're using the opposite sign on the x, or in this case the t, coordinate of the vertex. And our y-coordinate of the vertex, or in this case the maximum height, is the 25.921. 25.921. And then we've got an exact value. By keeping all of those digits there, we've got the exact relationship that's identical to the original relationship that was given.